Welcome for another mathematics lesson. We are going to do integration, whereby we're going to find the exact area bounded by curves and lines. So we're going to answer a question which says that in the figure below, the shaded region is bounded by the lines y equals to 3x, y equals to x, and the curve y equals to 8x minus x squared. The two straight lines intersect the curve at points P and Q. So we have P and Q, the points where this curve is intersecting the two lines respectively. The first question is to determine the coordinates of the points P and Q. These are the points of intersection of the curve and the two straight lines. Remember to subscribe to this channel and to share the link with your friends. So I'm going to use the space alongside the question. For the lines and the curve to intersect, then we have to say that the two equations are equal at the points of intersection, or rather we solve the equations simultaneously to get the coordinates of the points of intersection. Therefore, if we are saying a line whose equation is y equals to 3x and a curve whose equation is y equals to 8x minus x squared are intersecting at P, then the coordinates of P can be calculated by equating the two equations at this point. At this point, y equals to 3x, and at the same time, y equals to 8x minus x squared. So we can equate 3x and 8x minus x squared. In this case now, we can bring them together such that we have x squared, then we have negative 5x equals to 0. So we can factor out x to remain with x minus 5 equals to 0. Then at this point we can say now x is either 0 or x is equal to positive 5. And it is important to notice that the 2 points of intersection of this line and the curve are either at x equals to 0 and x equals to 5. But definitely, this coordinate cannot have x as 0, since x equals to 0 at the origin or at any point on the vertical axis. Therefore now, the coordinate of intersection of x is 5. We can get y at the same point where y equals to 3x. So we can say at the same point, y will be 3 times x, which is 5, to get 15. Therefore, the coordinates of P can be given as 5 and 15. We are told again to find the coordinates of x, whereby it is the intersection of y equals to x and the curve. So here we can equate x and 8x minus x squared, whereby we shall get x squared minus 7x equals to 0. And again we will have x and x minus 7 equals to 0. And at this point we can conclude that x equals to 0 and x is also equal to positive 7. Definitely at point Q, x will be 7 because x is equals to 0 at the origin. Therefore now, we can get the coordinates of y at that point by saying that y equals to x. Therefore, if y equals to x, then we can say y is also 7. Therefore, now we can say point Q as coordinate 7, 7. Therefore, we have the coordinates of Q and the coordinates of P. After that, we can look at the part B of the question, Roman 1. Calculate the exact area of the Roman 1 region bounded by the curve and the line y equals to x. Therefore, region bounded by the curve and line y equals to x, then is going to be the area below the curve, which is gotten by integrating this curve up to the point where we have Q. And at point Q, we have x equals to 7. Therefore, from 0 to 7, we can get the area below this curve. And now that we want area below the curve and line y equals to x, then we will subtract the area below line y equals to x. Therefore, we're going to get two areas here. First of all, we'll get area below the curve, which is going to be given by the integration from 0 to 7 of the curve 8x minus x squared. Then now after this, we subtract the area below this line, which is going to be the integration again from 0 to 7 of x, the integration of x. Therefore, to integrate this side, we're going to have x becoming squared, and we divide by 2, so that this becomes 4x squared minus x becomes cubed, and we divide by 3, so that this becomes a third x power 3 plus a constant. Then this is from 0 up to 7. Then we subtract area below the line, which is going to be x becomes squared, and we divide by 2. Then this is, we are adding a constant. This is from 0 to 7. From 0 to 7. Therefore, now we can fix the values of 7, and we also fix the values of 0. When we fix 0, we're going to get 0, except for the constant. But when we fix 7 for the first equation, we're going to get 81 and 2/3. 81 and 2/3. So we'll subtract, when we fix 7 here, squared, then we're going to get 49 over 2, which is 24 and a half. And this will give us a difference of 57 and a sixth. 57 and a sixth. These are square units. This one is the area bounded by the curve and the line y equals to x. After that, we're going to solve Roman 2 of the same question, which is on the next page. And Roman 2 is telling us to get the region bounded by the curve and the line y equals to 3x. The curve and y equals to 3x. So we shall integrate the curve until this point where it meets line y equals to 3x, and at this point x equals to 5. At p, x equals to 5. Therefore, we're going to integrate the same curve from 0 up to 5. And so that we may get the area below the curve and this line, we also get the area below this line. Then we subtract the two figures. So here we can have the integral to solve Roman 2. The integral from 0 to 5 of 8x minus x squared, and we subtract the integral from 0 to 5 of 3x. Of 3x, yes. So we're going to have 4x squared minus a third x cubed plus a constant from 0 to 5. Then we subtract. This one becomes 3 out of 2 x squared plus a constant from 0 to 5. Therefore, when we fix the values of 5, where we have x, we shall get 58 and a third minus this other side, we're going to get that 7 and a half. So that the difference between these two areas is going to be 20 and 5 out of 6. 20 and 5 out of 6. Now that we have the area between the curve and y equals to x, and also between the curve and y equals to 3x, Then we can proceed to solve part 3, which says the shaded region. And for us to get the shaded region, then we're going to solve the difference between the two areas, 56 and the 6th, 57 and the 6th, sorry, minus 20 and 5 out of 6. So this is going to give us a difference of 36 and a third square units. So that is the area of the shaded region. It is very important for me to highlight a few things. For example, area below these lines, we can use triangles, the triangle concept, whereby because we know the coordinates of Q is 7, 7, then we can say we have 7 units and 7 units, and we can use a half times 7 times 7, which is the height, so that the area of the triangle, say O and B, this one is Q, is going to be 24 and a half, the same value we got by integration. Again, we can also use, if the coordinates of P is 5, 15, then we can use 5 units and 15 vertical units, and we use a half times 5 times 15, and we will still get that 7 and a half, the same value we are getting using integration. So that is how we can get the area of the shaded region below a curve and some lines. Thank you for following. Subscribe and share the link.